For anyone new here, I am meteorologist Tanis Leach, and this is the first in what might be a series in the future called Pacific Northwest Weather 101. This is kind of like a test version of that to see if I want to do it in the future or not. And this first version of it is why the Pacific Northwest tends to not get thunderstorms. So back on August 17th of 2024, Western Oregon and Southwest Washington had a severe thunderstorm watch, which is incredibly rare. And unfortunately, I was out of town, so I was unable to post a forecast video. But that did inspire me to make this video on why the Pacific Northwest tends to not get thunderstorms. This picture behind that I'll be using in the background was from a thunderstorm on August 27th, 2023, and this picture has no filters. This is exactly how my phone took it in a screenshot from a video. And this was on my front porch in Sherwood. So they're possible, they just don't happen that often. Because when I'm looking at the annual mean thunderstorm days map posted by NOAA in their online school for meteorology, Jetstream, the Pacific Northwest and the California coast, plus the western portions of the Central Valley, is the only areas of the United States that are in this 0 to 9 day category, with specifically the Willamette Valley averaging about 5 to 7 days per year. So Portland averages 7, Eugene averages 5, and they're concentrated right around where the warmer months are, between April and September being the most common months to see thunderstorms, but there's a slightly sharper peak in May, June, and September, with May's records being 6 in Portland, 7 in Eugene, June being 5 in Portland, 4 in Eugene, and September being 6 in Portland, 4 in Eugene. And an interesting side note with October is, despite there not really being as large of a chance of thunderstorms in both Portland and Eugene, Western Oregon, Southwest Washington's tornado count is actually the highest in October compared to any previous month. And that most Portland and Eugene have experienced is 14 and 13 respectively for thunderstorm days. So going over the factors of what is required for a thunderstorm, you need three things: moisture, instability, and some sort of lifting mechanism or mechanisms, plural. So with the moisture factor, specifically warm moisture, it helps thunderstorms more often because warmer air holds more moisture, and warmer water provides higher levels of moisture to take from, because that generally keeps the air a lot warmer than it otherwise would be if you had for instance, in the Gulf of Mexico, where water temperatures are consistently 85 degrees during the summertime. The air temperature right over the Gulf of Mexico is not really going to fluctuate a lot, versus if on a similar land area that is 85 degrees, that's going to fluctuate. So it might get up to 105 on that day, but also cool down to 55, for example. So warmer air is also more conductive for thunderstorm development as well. And also, the Pacific Ocean tends to not provide enough moisture during the warm season, plus it is also too cold for typical thunderstorms. Now I'll be showing you this on a contoured sea surface temperatures. This was posted back on September 6th on NOAA's website. And normally during the summertime, we are under the influence in the Pacific Northwest from what's called the North Pacific High, which blocks a lot of low pressure systems from reaching our coastline. They generally get blocked northward, and any that do reach our coastline are considerably weaker, and a lot of times only just produce clouds and very little rain. But that's before we even look at the ocean temperatures. If we're looking at the ocean temperatures, Oregon and Washington are right at about this 18 degrees Celsius contour line, which translating to Fahrenheit, that's 64 degrees Fahrenheit, compared to the Gulf's current temperature, and they're in the 30-degree Celsius contour, which is equivalent to 86 degrees Fahrenheit, and that is the moisture that a lot of the non-tropical systems tap into for their thunderstorms. So there's a lot more moisture to work with than the Pacific Oceans. Second factor is instability. In the meteorological world, we consider the air unstable when an air parcel continues in the direction it is nudged. So, to simplify this, if it is nudged upwards, it keeps going up. If it is nudged downward, it keeps going down. So, generally speaking, per kilometer risen, you need about 6 degrees Celsius for it to be considered unstable, or 9.8 degrees Celsius per kilometer in a dry atmosphere. We like to call this the lapse rate. If it's anywhere in between, it is called conditionally unstable. And most of the time when we get thunderstorms, it is in this conditionally unstable form. So it is most common with differences in temperature via frontal boundaries, or if you could get warmer, moist air at the surface and cool, dry air aloft, which is pretty common, especially in the Great Plains during the summertime, as it's bringing up the warmer Gulf moisture and there's no mountains to block it, unlike moisture from the Pacific Ocean, which is why in Oregon and Washington, the western half of the state gets considerably more moisture than the eastern half of the state. Also, proximity to the Pacific Ocean's California current does also prevent these large temperature difference because the ocean, again, does provide a huge moderating influence. So along the west coast of every continent, there are cold weather currents. You see this with North America, you see this with Europe, you see this with South America, and you see this with Africa. And along the west coast of each continent, you have warmer ocean currents, and you see these on every major continent. So along the east coast of every country tends to be considerably warmer than the west coast of every continent. Moving on to our lifting mechanisms, because a thunderstorm does require an updraft to sustain it, which is fancy terminology for just upward moving air in a cloud. Common sources can include terrain forces, moisture slash clouds upwards, which is why the Cascades see thunderstorms more frequently than the Willamette Valley, especially in the higher peaks. Mount Thielsen specifically being known as the lightning rod of the Cascades. Differential heating can also cause updrafts to form, and in our area it is uncommon, but it has happened via a land or a sea breeze. Fronts, especially cold fronts, can cause these lifting mechanisms to occur, and while dry lines are almost unheard of west of the Cascades, it is possible to get a dry line. Dry line is a boundary between warm, moist air and hot, dry air. They're more common in areas of the desert southwest into the Great Plains. Then the last area of lifting mechanism involves outflow areas or battleground areas where colder air rushing in. And when a thunderstorm moves ahead, a lot of times that can create just enough updraft to sustain a weak thunderstorm for a brief period. This occurred during the snowstorm on January 10th through 11th, 2017, as there was a couple rumbles of thunder snow during that time as you got cold easterly winds pouring in with warmer southerly winds, and those winds met right around the Portland area, causing the air to get not only considerably more unstable than they otherwise would, but also increase the updraft and enhance the snowfall for that snowstorm. So back to our mean thunderstorm days and using these factors. So again, the mountains do block a lot of the moisture. So when we're factoring in a lot of the Gulf states here, because the Rocky Mountains don't block any of the moisture from the Gulf of Mexico, non-tropical systems that are moving west to east across the country can pull up moisture from the Gulf of Mexico all the way up into Canada. So that's why for similar latitudes, like for instance, take Wisconsin for example, you'd see about 30 days of thunderstorms per year at the same latitude compared to our 5. Then also because mountains see more thunderstorms, that's why the Colorado Rockies are shown having more thunderstorms than the Cascades, as the Cascades on the higher peaks are too fine in order for this map to show up any significant trends here. So moving on to our typical thunderstorm setup. The first setup is what is called a cutoff low, also known as an upper level low, most but not all of the time in this case. This is the Euromodel's reanalysis on August 17th, which was the day of the thunderstorm. And you could see here that there is a upper level trough, which is essentially an area of low pressure. And I'm showing the 500 millibar heights, which is essentially the height from sea level where you hit 500 millibars in pressure, which is about half of the standard pressure at sea level. So that trough is just to our southwest. And a lot of times when this occurs, it's able to bring in moisture from the south up into our area and over the Cascades and causes thunderstorms. This more commonly in the summertime causes nocturnal thunderstorms than it does daytime thunderstorms. But because there was enough moisture and instability, in this case during the daytime hours, it was able to create afternoon thunderstorms. And this area over here was the North Pacific High's current position, and that upper level low nudged it just enough further west in order to slide right in to bring us that moisture. And because we were coming out of a high pressure system that has slid off to the east, the Willamette Valley had a lot of heat to work with when that moisture rolled in overhead. But when you're looking at the surface map here, there's not really a significant low pressure center to look at here off the coast. In fact, there's no really contours of any circle to look at minus the North Pacific High here and what was Tropical Storm / Hurricane Ernesto in the Atlantic. So there wasn't really a low pressure center that was coupled with this upper level low here. And that's pretty common for this type of setup. And as a result, supercells are very rare in this setup. Normally, the biggest risk we see from this is hail generally up to a quarter size, maybe a little bit bigger, and some gusty winds, but tornadoes are not common with this. Most of our tornadoes actually come from low-topped supercells. So the second type of proper thunderstorm setup, and this tends to be a little bit more common on the fringe season, so April, May, and September, and this has to do with frontal boundaries. So specifically on April 5th, 1972, which produced a F3 tornado in Portland and Vancouver, we had an occluded front, which is where a cold front catches up to a warm front that extended it from the Oregon coast westward over to the low pressure center. And then a warm front passed through the Portland area first, but the warm front wasn't really super long. And behind the warm front, but not by too much, was the cold front. This created just enough instability because you had just a big enough pocket of warm air to be significant, but not so big that it stabilized the air or via Pacific Ocean influence. And also because they were so close together, that caused the winds also to come right up on the Cascade foothills and out of the Columbia River Gorge as well, which created a battleground zone in the Portland area and caused the tornadoes on top of some thunderstorms that day. So those are the two main setups that we tend to get. It's possible to get weaker thunderstorms in most setups that we see rain, but they're far less common than any of these two setups. Then the last thing I want to talk about is what constitutes a severe thunderstorm. So, when a severe thunderstorm warning is issued, that means the National Weather Service is expecting 58-mile-per-hour winds or quarter-sized hail, which is generally enough to damage at least some factors, generally windows, at that point. So when this is expected, they'll issue some sort of convective outlook. And for the August 17th severe thunderstorms, they issued a slight risk of severe thunderstorms for the Cascades and a marginal risk for the areas of the Willamette Valley about east of the Willamette River or going up into the Puget Sound area. This was also confirmed via the mesoscale discussion, where you could see on this polygon the area that the Storm Prediction Center was most worried about. A lot of times this polygon will translate into what will eventually become a severe thunderstorm watch, and they'll just shade whatever counties they're in. A lot of times, even if it's just a sliver. So most of these counties ended up being under that severe thunderstorm watch, even though, for instance, the entire Lane County was under severe thunderstorm watch. Areas west of Eugene didn't have as big of a risk of severe thunderstorms, and it wouldn't qualify it if they just did it by a pure or polygon. Severe thunderstorms are pretty rare with, don't quote me on this, but I believe in the past 3 years there has been about 10 severe thunderstorm warnings issued by the Portland National Weather Service office. So far less common than anywhere out east. But that is my lesson to you on thunderstorms in the Pacific Northwest, at least the crash course version of it. Hope you enjoy this. Let me know if you want any more of these type of videos. I may just do them anyways, just to have in my back pocket in case I need to reference them for future videos. But the next video that I expect to come out with will most likely be my long-range winter weather forecast on the 4th week of October, so stay tuned for that. But until then, stay safe out there and take care.